Hi, everyone. Okay, so in this lecture, we're going to give an extension of extended Euclid, and then we're going to also look at modular division. So the question to motivate an extension of Euclid's algorithm is, how do we verify that a number D is the greatest common divisor of A and B? So if I give you a number D and I claim it's the greatest common divisor, how do you tell? How do you check that it is? I guess you could run Euclid's algorithm and check that you get the same value, but we can do it kind of all at once. And so to do that, we have the following. So if D divides both A and B, that's necessary for it to be a candidate for the greatest common divisor. And D can be written as AX plus BY for some integers, X and Y. Then necessarily D has to be the greatest common divisor. And notice that these X and Y could be negative numbers. They're integers, but they could be positive or negative. So why is that true? So first of all, by this first statement, D divides both A and B. So we must have D is less than or equal to the greatest common divisor of A and B, since D is a divisor. Also, the greatest common divisor of A and B divides AX plus BY, since we know that the greatest common divisor divides A and the greatest common divisor divides B, right? So A can be written as P times the GCD of A and B, and B can be written as some Q times the greatest common divisor of A and B. And so that then means that this is D, right? So that means that GCD of A and B is less than or equal to AX plus BY, which is equal to D. And so now you see we have D is less than or equal to the greatest common divisor, and D is greater than or equal to the greatest common divisor. And so that implies that D is equal to the GCD of A and B. Okay. So if we could write D in this form, if we could write the greatest common divisor in this form, AX plus BY, where A and B are the numbers that we're finding the greatest common divisor of, then we can, that's a kind of proof that that is indeed the greatest common divisor. And we can actually compute those coefficients, X and Y. And this can be done using the extended Euclid algorithm. So it takes in A and B, where A is greater than or equal to B, same as just the regular Euclid's algorithm. And it outputs integers, X, Y, and D, such that D is the greatest common divisor and AX plus BY equals D. And the way it runs looks a little bit unusual, maybe. So if B is 0, we return X is 1, Y is 0, and D is A. And otherwise, we make a recursive call, kind of like what we did with Euclid, right? Where the second argument becomes the first, and the first argument, we take A mod B. And that's the first becomes the second, but we mod it with B, right? And then we return this kind of interesting combo. We return Y prime, where Y is the second argument. We return that as our X. We return X prime minus the floor of A over B times Y prime as our Y, and we return D. So the first thing you can verify is if you look back at the last lecture, The third argument here, D, is the greatest common divisor. And this logic looks identical to Euclid, right? If you just ignore the X and Y part, if the argument B is 0, you return A. Otherwise, you call Euclid on B, A mod B, and you return the result. Right? The only thing we have to kind of figure out is what's going on with X prime and Y prime, and why is this computing the right numbers? So this is, I think, the first time in this course where correctness of the algorithm is not so clear, right? Trying to understand the logic here is complicated. So now I'm going to give like the statement for any positive integers A and B, the extended Euclid algorithm is correct. That means it does indeed compute an X, a Y, and a D satisfying these conditions. And the way I'm going to kind of argue this is a bit informally, because then I'll tell you how we would prove it more formally, and then we'll actually do a little bit of review to solidify that. So let me say, just kind of repeating what I said there, is first note the GCD of A and B equaling D is correct. Ignore the parts dealing with X and Y. And it is identical to the Euclid algorithm we gave in the last lecture. So now let's try and understand what's going on with this algorithm. So let's suppose that the result on line 3 is correct. So the result here is correct. Okay. And by that, I mean that the X, the Y, and the D are correct. Right? Sorry, it's actually X prime. Sorry, X prime, Y prime, D prime, right? Or X prime, Y prime, D. The D does not have a prime on it. Now, just that means that X prime multiplying B plus Y prime multiplying A mod B equals D. Right? That's just by the definition of what the extended Euclid does. Right? X prime times the first argument plus Y prime times the second argument has to equal D. So now, but recall that A mod B is equal to A minus the floor of A over B, B's. And so I can replace this here with this expression. So then I get X prime B plus Y prime A minus the floor of A over B times B equals D. And now I want to rearrange it so that I get a term multiplying B and another term multiplying A. So if I look at what multiplies A, I get Y prime A And then what multiplies b? It's x prime minus x prime minus y prime floor of a over b. And that all multiplies b. That equals d. And so this then is my x, and this is my y, right? And this is my d. And then I have it written as ax plus by equals d. And so we see the x, y, d equals y prime, x prime minus y prime floor of a over b, oops, and then d. And that's exactly, if we go look back up, y prime, x prime minus floor of a over b times y, d, that's exactly what gets returned by the algorithm. So this matches the algorithm. So this isn't quite a proof. I'm kind of giving some intuition because basically I'm supposing the result is correct. And then I'm showing that if it was correct in line 3, then it's correct in line 4 of the algorithm. So the way to do that more formally is through induction. So to make formal, use proof by induction. And so, and in particular, induction on the second argument, on second argument, b. And so in this, you get that the base case is b equals 0. Right? And then that's easy to show that it's correct because that just looks, that's returning this. And you can see that it's then going to return a times 1 plus 0 times b. So a equals, and then the d argument is a. And the greatest common divisor of a and 0 is indeed a. So this is correct. Base case is b equals 0. This I'll just say here is easy to show. And then we assume it holds for all b prime less than b. Show it holds for b. And that's the argument. That's the argument above. So combined, those two are able to prove the main result. So I'm going to give a bit of a review of induction, just a quick one, in case, you know, probably a lot of you haven't used that in some time. And so I think it's useful, but that's sort of the intuition behind it and then how you can formalize that intuition. Now, let me give you an example of computing the greatest common divisor with this algorithm. So let's start by doing it with just Euclid's algorithm. So from Euclid's algorithm, we have that to compute the greatest common divisor of 30 and 14, we instead compute the greatest common divisor of 14 and 30. mod 14. What's 30 mod 14? Well, 14 goes into 30 twice with a remainder of 2. So that's the greatest common divisor of 14 and 2. Right? We apply the same thing. The second argument becomes the first. And we take the first argument mod the second and write that as our second argument. So then we're going to get 14 mod 2. And 2 divides 14. So this is equal to the GCD of 2 and 0, which is just equal to 2. So the greatest common divisor of 30 and 14 is 2. To find x and y, we would need to call extended Euclid. And we have the same recursive calls, right? It goes, so same, which is that first we call GCD of 30 and 14. That then calls another calculation on 14 and 2, which calls another on 2 and 0. And in extended Euclid, we recurse down to the bottom, right? And then we kind of come back up, filling in the calculations. So for the GCD of 2 and 0, we have the first argument. So A is equal to 2, B is equal to 0. And we return x prime, y prime, d is equal to 1, 0, and then A, right? 2. That follows from the base case here, right? 1, 0, A gets returned. Now, for the next level up, 14 and 2, we have now A is 14, B is 2, and I'll call it X double prime that gets calculated there, Y double prime, and D. That's going to be given by Y prime, X prime minus the floor of A over B, Y prime, and D. This is equal to, well, Y prime is 0. X prime is 1 minus the floor of A over B times Y prime, but Y prime is 0. So this is just going to be X prime, which is 1. And then 2. And then finally, for the GCD of 30 and 14, we have A equals 30, B equals 14, Y, the final result, X, Y, D, is given by Y double prime, X double prime minus floor of A over B, Y double prime, and D. And that's equal to, well, Y double prime is 1. X double prime is 0. So this is going to be 0 minus the floor of A over B. 30 divided by 14 goes in twice. So this is minus 2 times Y double prime, which is 1. So we're going to get minus 2 and then 2. And then notice we can verify that this indeed satisfies AX plus BY is going to be 1 times 30 minus 2 times 14, and that equals 2. And so this indeed is a correct calculation of the coefficients x and y. Okay, that is extended Euclid. It seems quite abstract. I totally agree with you if that's how you're feeling. However, we're going to apply it in the next lecture directly to solve RSA cryptography, or to build what is RSA cryptography, which is like, used ubiquitously on the internet. I'll show you just some examples of, like, every encrypted website uses RSA to exchange keys. So it seems abstract, but it actually builds something pretty neat, I think. So now I talked about above that we would apply induction in order to prove the extended Euclid algorithm was correct. Let me just quickly review induction for those of you who haven't seen it in a while. So if we want to show some statement, I'll call it S of k. So it's some statement that's a function of an integer k, holds, and I want to show it holds for all integers k. The way we do that is we show it holds for S0, so a base case, right? It generally will be S of 0, but it could be S of 4 or something like that. And then we say, suppose it holds for Sk, then we can show it holds for S of k plus 1. That's called the inductive step. So we basically just have two steps, the base case and then the inductive step, which is assume it holds for k and show it holds for k plus 1. And so that means if it held for k, that would imply it holds for k plus 1. And if you can do those two things, then you've shown it holds for all k. And the reason why is that you've basically created a chain of logic. So you verified by hand in the base case that it held for S0. Through your inductive argument, that shows that if it held for S0, then it held for S1, right? That gives you this implication. But then now that you know it holds for S1 and you apply your inductive step again, that shows you that it holds for S2. And that just continues along, right? And you've shown that it holds for all Sk. There are times where to show that it holds for Sk plus 1, you need more than just Sk. Like you might need to apply that it holds for Sk, Sk minus 1, Sk minus 2, Sk minus 3 in order to show it holds for Sk plus 1. For this, we use strong induction. It's the same thing, but instead, in strong induction, the step becomes if it holds for all k bar less than or equal to k, then it holds for k plus 1. And that's actually the type of induction that we would apply in proving extended Euclid more formally. So let me just remind you with showing that this sum is equal to n plus 1 times n over 2. So the sum of j from j equals 0 to n is equal to this. So what do? We start with the base case. I'm going to show it my base case as n equals 1 because n equals 0 is not interesting. The left and right hand side are 0. But for 1, we have the sum from 0 to 1 of j just equals 1, which equals 2 times 1 over 2, which equals n plus 1 times n over 2. Right? Because n here is 1, so that n plus 1 is 2, n is 1. So it holds for the base case. Now we do the inductive step. So we suppose the result is true for n. And then we show for n plus 1. And to show for n plus 1, you're going to leverage the fact that it holds for n, right? And what you're trying to do is when you try and show for n plus 1, you like break it down into the part where you can apply that you know it holds for n, plus some additional thing that you can figure out directly. And so that looks like this. So for n plus 1, we have the sum from 0 to n plus 1 of j. That can be written as the sum from j equals 0 to n of j plus the final term, which is n plus 1. Then we apply the inductive hypothesis, which is that it holds for n. And so that's just going to be n plus 1 times n over 2 plus that last term, n plus 1. And then we just group, like we make a common denominator, right? I mean, you can see if we multiply this by 2, top and bottom, and then sum it, then what we end up getting is n plus 2 times n plus 1 over 2. And here, this is where we applied our inductive hypothesis. And so we showed that it holds for n plus 1. And with that, now we've shown this result for all n. Okay. Last thing I want to cover in this lecture is modular division. And so remember I said that modular multiplication was kind of, we could just use our multiplication algorithm followed by dividing by n to find the remainder. Modular addition, we just added the two numbers and then we subtracted n off of it. But modular division was interesting because sometimes you can, like, if I want to divide x by y mod n, sometimes it's an integer and sometimes it's not, essentially. And so I'm going to formalize this idea. So an integer x is the multiplicative inverse of a modulo n if a times x is equivalent to 1 modulo n. Right? So when I multiply a by x and take mod n, I get 1. There's a few things. For a given a, there can be at most one inverse in x in the range from 0 to n minus 1. Additionally, for some a, there is no multiplicative inverse. So I don't know if you can think of an example where there won't be a multiplicative inverse, where this equation has no solution. So think of an a and an n where you can't find a solution to it. One example is take 2x, and there's no way 2x is never equivalent to 1 mod 4. Right, plug in x equals 0. On the left-hand side, I get 0, which isn't equivalent to 1. If I plug in 1, I get 2. I mean, another, quickly stating it without plugging in 0, 1, 2, 3, is the left side's always even, the right side's always odd, right? Even mod 4, it keeps the left side even. So there's no solution to this equation. So then you can ask, for what values of a and n is there a multiplicative inverse? So recall, ax equals or is equivalent to 1 mod n if and only if we wrote this before, n divides ax minus 1, right? You take the left-hand side minus the right-hand side, and n must divide that. that means that ax minus 1 can be written as an integer multiple of n. So if and only if ax minus 1 equals minus y times n, for some integer minus y. I'm only writing this as minus. You might write it just as y, not minus y. I'm writing it like this because it's going to end up being clearer in a moment. But you could just think of it as this is just an integer. For some reason, I'm using the symbol minus y for the integer. But the reason is that I want to rearrange it. And so that's the same as saying ax plus ny equals 1. But now this, we know that 1 divides both a and n. And so this equation means that the greatest common divisor of a and n is 1. Greatest common divisor of a and n equals 1. This is by Euclid's. Or by the lemma on Euclid's algorithm, or by the property we gave before Euclid's algorithm. And so an inverse exists if and only if the greatest common divisor of a and n is 1. And this has another name. So this is the same as if and only if a and n are relatively prime, or coprime. So you can see here in this equation, a is 2, n is 4. Their greatest common divisor is 2, which is not 1. So these two numbers are not coprime, and that's why this doesn't have a solution. If instead I said 2x, is 2x equivalent to 1, like is there an x for the equation 2x equivalent to 1 mod 3? The answer would be yes, because 2 and 3 are coprime, right? 2 and 7, 2 and 9, right? Anything like that. So therefore, A has a multiplicative inverse modulo n, if and only if the greatest common, not denominator, divisor, of a and n is 1. That is, if and only if a and n are relatively prime or coprime. And the other thing that you notice is that if a and n are coprime, we can actually find the multiplicative inverse using Euclid's algorithm, because Euclid's algorithm will give us x and y, and you can see that x is the multiplicative inverse. So the only little issue is that in Euclid's algorithm, we always input the bigger number first. So instead of inputting it as a and n, we would input it as n first, followed by a. And so then the greatest common divisor will be the y, essentially. So let me just summarize that. So for any integer a in 0 to n minus 1, a has a multiplicative inverse mod n, if and only if the greatest common divisor of n and a is 1. When the inverse exists, it can be found in n cubed time as y mod n, where y comes from extended Euclid on NA. So I'll just write here, we put n first since it is larger. it would be X if we called extended Euclid on AN instead, right? Like just like what we had here where AX. But the thing to remember is basically I can compute if there's a multiplicative inverse, I can just compute it from extended Euclid. And let me give you then an example. So let's say that A is 11 and N is 25. So if I call X, Y, D or I call extended Euclid, put the bigger argument first. So on 25 and 11, right? This is N, this is A. The result, if you calculate it, and you can check this after, is 4 minus 9, 1. And so the multiplicative inverse of A modulo N is going to be Y mod N, which in this case is minus 9 mod 25. Minus 9 mod 25 is 16. And we can check this. So if I want to go AX mod N equals 1, the numbers that I have are A is 11 times 16 mod 25. And we know that's true if and only if 11 times 16 minus 1 divided by 25 is an integer. But 11 times 16 minus 1 is exactly 175 divided by 25, which equals 7. So that is indeed an integer. So 11 times 16 is 176. 176 mod 25 gives you 1. Goes in 7 times with a remainder of 1. So this is how we compute the multiplicative inverse of a number when it exists. So we check if it exists by checking if A and N are coprime. If it exists, then we can call extended Euclid on NA. We look at the second argument that we get from extended Euclid, take mod N so that we get a mod N number. Of course, A multiplying minus 9 mod 25 will also give you 1. It's just that it's not then we just want to map it to its equivalent number between 0 and N minus 1. And that's why we take mod N here. Okay, so in the next lecture, we'll finally wrap things up. We're going to go through generating a prime number, generating large prime numbers, how we do that, and then RSA cryptography. And that will wrap up this chapter of the course. So thank you everyone for listening. And this is the last lecture for the week, and I'll see you next week.